So I'm going to address air approaches to climate resilient agriculture in the Northeast. And maybe Northeast is a little broad. I think maybe New England is a little more appropriate for this talk. And then maybe more specifically Vermont, because that's of course where I'm working and the stakeholders that I'm trying to serve in my position. Just to give you a quick snapshot of Vermont agriculture, about 75% of marketable goods are dairy products, and those are most of those are produced by conventional dairies. The remainder of the ag sector are a kind of a very, in many cases, progressive, younger, newer, beginning growers, and so we have these very diverse stakeholder groups that we're trying to help meet the challenges of climate change. Just to give you kind of a frame of reference for some of the things I'll be talking about. So let's just jump right in. In the Northeast, we've seen about a little over a 4-inch increase in precipitation over the past century. I think for most farmers, this really is manageable. It's not a showstopper. They can kind of take this in stride. The interesting thing is, though, that across the Northeast, this is not necessarily distributed evenly. In the northeastern region of Vermont alone, they've seen in the past 40 years a 9.5-inch increase in precipitation on average, and so this is significant. This is almost a 25% increase in precipitation, and the farmers do notice this, and they are taking measures to adapt to this increased precipitation. So there's this annual increase. I don't think that's, to me, that's not the priority, that's not the challenge. The number one challenge, the challenge is how that precipitation is coming. And it's really coming in, here we go, in these increased frequency of intense precipitation events. And this is you know, it seems that the Northeast is really getting the brunt of this nationwide with a 74%. And actually, I just, there's an updated figure that's in the National Climate Assessment that goes through 2012. This is through 2010, but that 74% reduces to about 71% using updated data through 2012. But regardless, there's certainly noticeable increase in extreme events in the Northeast, and this is our top priority, and this is what farmers are concerned about. This is really why the position I hold was created, and so this is what I'm tasked with working on. On-farm impacts of these increased intense events are of course increased soil erosion and nutrient export from the fields. I don't know if you can tell, I got a pretty big grin on my face right there, and I probably shouldn't. This is just something kind of as a soil and water resources engineer you see in textbooks, but it's very rare that you get to stand in a gully that's mid-thigh in a field and you know, kind of in person. So this was kind of cool. Definitely not cool for the farmer. This was sweet corn, a very high value crop for him, and he lost maybe a 1/4 acre of soil there, up to maybe a 2.5, 3 foot depth in places. This is from one rain event last summer, early July. And there's been some modeling work done by Mark Nearing and his colleagues, where they've estimated, this quote right here is from one of his papers, where as we see the annual rainfall increase, that we'll see erosion increase at a proportional rate, 1.7 times. So thinking about northeastern Vermont, where there's a 25% increase in annual rainfall, that's over 40% increase in soil loss. And that makes, you know, that certainly throws a flag up for me and presents a significant challenge for farmers. This is some more modeling work done by the same group in 2000, I think it's a 2005, O'Neill and Nearing and some others. This is from the Midwest, but they compared a 1990, 1999 time frame to a 2040, 2049 time frame, accounting for climate change, and looked at soil loss between those 2 decades. And in some instances, significant increases in soil loss. And you know, this is from the Midwest, upper Midwest, but to us, as we think back of that, at that regional distribution of intense storm events, with the Northeast having more than the rest of the country, we certainly can expect this, if not greater, a greater increase in soil loss from our farms. So this is what we're, the infill impacts, but also there are a number of downstream impacts from these intense events and increased precipitation, flooding, as well as water quality impacts on receiving waters. This is kind of an interesting, this guy right here is a little bit of the poster child for flooding in Vermont. This is following, this picture was taken just after Hurricane or Tropical Storm Irene, and he lost not just soil from his fields, he literally lost acres of ground. So these farmers that are really confined to the fertile soils in the floodplain in these hilly mountainous areas, we're trying to work with them and help them adapt as well to these precipitation events. This is an aerial shot just again after Tropical Storm Irene of the Connecticut River, kind of belching its sediment load into the Long Island Sound. And this quote at the top, or this statistic at the top by some folks at Woods Hole and USGS is just, to me, staggering. 2 events, and we had 5 times the annual average sediment load into the Hudson in 2011. And Tropical Storm Irene kind of went up part of the Hudson Valley, then it shifted a little to the east, and so the Connecticut and the Hudson both received a considerable amount of erosion and sediment, not both from agricultural fields, but also due to in-stream bank erosion. So the other, kind of the gorilla in the room as we think about climate change adaptation for our farms is a new TMDL that was, I think it was a week and a half, 2 weeks ago, was finalized. A revised TMDL was finalized for the Lake Champlain Basin. And so we know that the expectation is to reduce total phosphorus loads in the basin by about 36%, and agriculture is responsible for about 40% of the load to the lake. And this is some work that was done in the development of the TMDL, where the blue bar on the left is the baseline, not accounting for any climate change, and then all 6 scenarios to the right of that are taking into account different climate change scenarios. And you can see that the total phosphorus load is certainly expected to increase with climate change. And this just adds to our kind of the urgency to address non-point source pollution because of these precipitation and extreme events. This also is pretty interesting. This is as we see surface waters warm, we know that they'll become more susceptible to incoming nutrients and sediment. The top graph is the Lake Champlain ice over the past 100 and some years, and the red dots there at the bottom of the chart are years when it did not ice up. So starting in about 1950, you had very few years from then on where the lake iced up. And the impact of this is that in the spring the lake tends to stratify earlier if there's no ice on the lake, and that warmer water sets up on top. And it's in eutrophication. The kind of the time frame when eutrophication can occur is much longer, almost a month longer now than it was in the 1950s and 1960s. So this is how my program kind of envisions or has laid out our approach to agricultural resilience. Like I said, from a soil and water resources perspective, number 1 being increasing landscape storage, and I think that's where kind of the concept of green water and blue water fits really well with some of the work we're doing, and I'll talk more about each of these individually, as well as we're also working on floodplain strategies for those farmers that are producing in the floodplain, trying to reduce their risk and keep them productive. And then number 3 is just basic water management for production, something I think Extension has done for years and years. I'm very conventional things like helping farmers with irrigation, helping farmers with drainage, but how farmers manage water on their land to improve production. And then the fourth one, which I won't spend much time on, but I think is very important when we think about the increased nutrient loading due to climate change, is increasing adoption and redoubling our efforts at some of the conventional best management practices and nutrient management on farms. I think this is certainly something we're thinking about and concerned with, and will continue to do outreach around. So increasing landscape storage capacity, and it's I don't know if anyone heard the plenary this morning from Peter, who kind of framed this green water reservoir in agricultural soils, and that sets this up really well, because that's what a lot of what we're trying to work on, and is trying to increase the amount of water that infiltrates into our soils, not necessarily for drought resilience, but just to reduce the amount of runoff and all the benefits that come with that, from nutrient cycling to reducing peak flows in channels, reducing stream bank erosion, and so on and so forth. There are a couple ways of doing that, some management approaches and some structural approaches, and I'll try to go through some of those. For me, as a soil and water resources engineer who's typically worked at the edge of field, dealing with the water that comes off of the field, I think this requires kind of stepping into the field and building kind of interdisciplinary working relationships with soil scientists and agronomists and plant scientists, and trying to, if we're going to handle water at the edge of field effectively, working with the practices in the field that can reduce the amount of water that we do have to deal with when it comes off. You know, we kind of think about a lot of the parlances around agricultural runoff, and I think, sure, that's an issue, but I think maybe we need to shift our focus towards agricultural infiltration and work towards increasing that, and then runoff won't be such an issue. So really, three basic concepts, and these are concepts that are kind of embodied in some of the NRCS soil quality initiative outreach that's occurring across the country for the past year or so. And soil cover is primary here, and there's been, you know, just scads of work on how soil cover can increase infiltration. I'm not going to go through the data, but we know this happens. These are physical effects of soil cover, and certainly we can reduce agricultural runoff and increase our landscape storage if we keep our soils covered. This is a I don't know how well you can see that. This is a tool that if you ever get a chance to see one of these rainfall simulation displays, I highly encourage to go check it out. You basically take slices of soil from different management across, you know, you can do this on one farm or many farms, but this one here on the left, this is probably the most dramatic difference you can show with this tool, and these are two samples, both from conventionally tilled cornfield. One just has some mulch on it, and we rain on this and catch the runoff, and in the front bucket here, and you can see that there's virtually no, or there's just an inch or two of water in this bucket, and this bucket filled up entirely with water and sediment. Just taking those landscape processes, what soil cover can do at the landscape, shrinking it down to a scale where people can see and understand. And it's incredible when you see the light bulbs go on when farmers and others see these demonstrations in person. Kind of the second concept that we're working with is just reducing tillage, and again, nothing new here. This is we've known that this can help improve infiltration for years and years by building soil structure and encouraging macropore formation and getting water into the ground where it doesn't run off. Plenty of data on this, but surprisingly little reduced tillage and no-till at least in Vermont. Organic matter is the third one, and increasing the amount of soil organic carbon. It has some mitigation benefits. That's a tough sell for farmers to try to talk to them around around mitigation and storing carbon. I think it's much easier to talk to them about what organic matter can do for production. And of course, to me as a water person, I'm very interested in what this can do for infiltration. And again, lots of data on this and good supporting evidence. So those are the managerial approaches. There are also structural approaches to landscape storage. One we're very interested in and starting to do some work in Vermont on is what's the benefit of multiple small storage structures distributed throughout a watershed on flood resiliency. And this is something that I think inherently, as water people, as engineers and hydrologists, we understand there is a benefit here, but trying to quantify that and maybe develop some thresholds at which maybe further implementation of small farm ponds and dams can have a benefit to downstream communities. This is a real example of how some folks in New York, Peter Wright with the NRCS there and Art DeGaetano at Cornell, have used climate change data to update their design procedure for on-farm storage structures, wastewater storage structures on dairy farms. And they've basically taken data starting back in the late 1800s and parsed it out into 3 different time periods and analyzed how winter precipitation changes during the winter over those 3 time periods, and have you can see in the last graph here it trends upward a little bit over the past 30 years, and so they've created some maps and updated their design guidance for dairy farms to increase the capacity of these on-farm storage structures. This is another example of improving landscape storage capacity with on-farm structures. So we've looked at, there's been a lot of work around increasing the ability of rainfall to infiltrate in urban areas, and so we also have some impervious areas on farms. Heavy use areas being certainly one for beef cattle or dairy cattle. And so we've started to install some absorbent heavy use areas. So instead of the expense of concrete, we've built these with large wood chips, which tend to absorb the incoming precipitation and then re-evaporate it, dramatically reducing the amount of runoff and nutrients that we have to deal with off of that heavy use area. And then controlled drainage. This is something we're just now starting to ask some questions about and starting to look into as we see there's just this wave of drainage tile installation, at least in the Champlain Valley, and we're curious how this drainage tile installation is going to influence flooding in the basin, and maybe there's an opportunity for coordinated networks of controlled drainage structures where we can actually build reservoirs, quote-unquote reservoirs within the soil, if we can anticipate events before they and release water from the soil and then close our gates and be able to store that water within our soils. So some of the questions we're starting to ask and think there may be potential for. Floodplain strategies, of course, flooding is inevitable. I don't think landscape storage is going to solve all of our issues. This is a shot following Tropical Storm Irene, devastating not just losing land and destroying crops, but also infrastructure, something farmers are very, very concerned with. River management is put forward by our state agencies as a prime strategy to increase resilience, at least for communities, to flooding. And this is a graph that's somewhat the poster child for river management. This is the hydrograph in Rutland and Middlebury on the Otter Creek, just following Tropical Storm Irene, and where the peak flow was dramatically decreased downstream of Rutland and attributed to very extensive networks of restored riparian wetlands and the flooding that took place in farmers' fields between these two cities. And that's fantastic, but I think it's a question that I can't answer, but this is certainly a service that farms provide for communities when they allow their land to flood and they lose their crops and there's no compensation for them. So farmers are asking these questions: what's the benefit? Is there payback for the ecosystem service that they're providing to those communities? And some farmers are even selling their land and moving to higher ground to avoid this flooding. So multifunctional riparian buffers. This is a concept that we're very interested. It's a little bit out of the box, but we're starting to have a couple of these, install a couple of these on the ground in Vermont. And the concept is that by installing riparian buffers and displacing crops from the near stream area, we reduce risk to the farmer. Of course, the farmer still wants to have some economic return from that ground, so we're trying to design riparian buffers that have some sort of harvestable crop within them. There are a number of ideas here, but buffers that also provide the important ecosystem services that we traditionally associate with them. This is a good example of one of those. This is on the main stem of the Lamoille in northern Vermont, and this is probably one of the top 3 vegetable producers in the state. He has some very productive fields down here along the Lamoille, and this red crosshatch is right in the floodway. And he's worked with state agencies to take a 35-foot buffer out of production if they'll allow him to plant 15 feet of native riparian buffer against the stream corridor, and then 20 feet of elderberry from there on in, allowing him to get some economic return from that buffer. He believes there's a strong market because of the number of processors using elderberry within Vermont. Elderberry, of course, a riparian species and certainly resilient to flooding. Our questions are kind of centered around what are the ecosystem services provided by buffers that are harvested, and so some pretty interesting work I think we have ahead of us. And then this third focus of our work is this traditional role for extension. Like I said, water management for production. Irrigation is probably first and foremost on our in terms of what we're addressing this summer. Drip irrigation is of great interest to our producers, not only for climate resilience, but also for food safety reasons. If the water doesn't come into contact with the edible portion of the plant, there's the stipulations on water testing are not as strict. And we see that there is an expectation that Vermont will see increased drought and increased irrigation withdrawals. This is a great paper from 2013 that kind of ranks all the states in terms of how the withdrawal of irrigation will change from 2005 to 2090, and Vermont's right there in the middle of the pack. Even though we're getting wetter, we're expected to have droughty periods through the summertime, interspersed by these intense storms. And then subsurface drainage. There's just, like I said, you can drive around in the wintertime, and there's just tile line sitting in the fields ready to go in as soon as things get dry, and it really is going in like gangbusters. And so it's a prime opportunity to work with producers, make sure we're doing this responsibly, and maybe encourage producers to install some of the nutrient mitigation practices, such as bioreactors and controlled drainage that are out there and can be cost shared through the NRCS. And then, like I said, just a redoubling of our soil and nutrient kind of efforts and nutrient management on farms. To me, it's an encouraging thought that if farmers are installing these practices to adapt to climate change because they have to, we've been pushing these BMPs for years with mixed results of adoption, and maybe we'll see payoff in water quality because farmers are need to adapt. So that's kind of encouraging to me. And then outreach and education, of course, is important. And I think that this is a quote from an extension specialist in Wisconsin. I like to, I think about every time I go out and work with stakeholders, and I think it's very true depending on the group, knowing your audience, and I think it's important to meet farmers where they are, and to try to work with them, and be cognizant of the terminology you use. And then, of course, always we need to be present and at the table for policy discussions. So thanks. That's all I have. Do we want to questions now, or?
We can take a couple now, and then we'll have time to answer.
Yep. Okay.
We can take a couple questions, and I'll switch to
Okay.
the next one while you answer. Okay, sure.
Yeah.
Thank you. I'm curious about whether there is research on pollinator support and integrated pest management in properly designed and better designed filtration and buffer where the drainage is most likely to take place. I'm thinking of Michael Doskey's work at the Agroforestry Lab in Lincoln. I don't have a connection yet to pollinators and IPM, but I suspect that if you take that same volume of space or area of space and put it into more concentrated forms where the drainage is most likely to be intercepted, and that's topographically determinable, there would be substantial ecosystem service benefits as opposed to the traditional strip, which is terrain insensitive. And my second allied question is Vermont ahead of the game because it has a substantial farm base which is not on the rectangular grid? I'm thinking of how important it may be for the rest of the country after the Northwest Ordinance to get off of the rectangular grid to be able to use terrain. So IPM and pollinators is one question, and the other is the way the land is literally physically divided and whether that's advantageous in the Northeast compared to other places. Thank you.
Those are good questions, and I don't work a lot with pollinators. I can say I know there is some guidance out there on what species to use in buffers, and we have used that information. I believe it's published by the NRCS state by state, and so we've certainly referred producers to that guidance. And I will just second your comment. I'm very much in favor of variable width buffers that are cognizant of flow paths. And that's something that, I think we're very in favor of that. It's just how programs work and whether programs allow for that. And that's kind of, so in some ways we're limited by the agencies in the way they've structured their programs in terms of buffer width and design. In terms of the shape of fields in Vermont, I think, it's, if you go to the Champlain Valley, I think there are a great deal of very square and rectangular fields too. So I think it's, it's kind of a toss-up in the rest of Vermont. Out of the valley, it's, the fields are in the floodplain, and so of course they're not as square and rectangular.